Okay, welcome to Chapter 5. We're dealing with probability. We're dealing with discrete probability distributions. The end of the chapter will be our introduction to binomial probability distributions. They're also discrete, but they're of a particular kind that comes from a fixed probability. First thing that we want to remind ourselves of is the random variable. We're going to refer to the random variable as x, and it's going to represent the quantitative variable, that is a number, that is measured or observed from an experiment or a study. We also want to remind ourselves of the difference between discrete and continuous. This is basically the difference between Chapter 5 and Chapter 6. Chapter 5 is discrete. Chapter 6 is our first look at continuous distributions. So what is the difference? There are different types of quantitative variables called discrete or continuous. Discrete data can take on only particular values in a range, while continuous data can take on any value in that range. So for example, discrete data usually arises from counting, while continuous data comes from measuring. My height isn't a perfect number of feet. It can be measured with more detail. It's in a range, whereas my age might be considered to be discrete, or the number of people in a household. So our next example looks at the result of the 2010 census and the number of people in households. This is discrete. It's discrete because the household values can only take on 1 up through 6 and 7 and more. So there's no way of talking about a half of a person in this context. So for example, this says that 26.7% of households in the United States at the time of the 2010 census had only one person living in them. And similarly, 33.6 for 2 people, and all the way up to 7 or more. So you might look at this and you might say, well, this is a observation. This is taken from asking people how many people live in their house. And in a sense, this is a true discrete probability distribution. There is no underlying probability that different households have different sizes. We simply went out and measured. Now, for a discrete probability distribution, that is, for a discrete probability distribution that is not binomial, the mean is exactly what you'd think. It's simply x times the probability of x and then added up. Remember that capital sigma that looks like the capital sideways M says to add up all those x times p of x. So x, of course, is the random variable. In that first case, x was 1. The probability was 0.267. So we'd multiply those together, then we'd multiply 2 times 0.336. We'd multiply 3 times 0.1518. You get the idea. And continue in that way, and then add them up. We don't add up last because of the order of operations. Now, the mean also tells us our expected value. So if you're asked how many people would you expect to be in a household in the United States at the time of the 2010 census, you'd compute the mean. The standard deviation looks very similar too. It's simply saying to find that difference between each of the x values, each of those random variables, and the mean. Square that just like we did before, multiply that by the probability of that random variable, add all those up, and then take the square root. We have to take the square root to undo that squaring that we did. Now let's take a look at doing this in our calculator. So here's our calculator, and let's go through and compute the mean and the standard deviation for this data. So the first thing we're going to do is go into the Stat menu. We're going to leave Edit selected and press Enter. We're now going to load this data. I've already loaded the household sizes, so 1 through 7. So now I'm going to load the probabilities. So I'm looking at, for household sizes of 1 people, I'm seeing 0.267. I'm going to enter that. Then I see 0.336. Then I see 0.158. Then I see, we're now at 4.137. We're now at 5. I need to enter that. 0.063. I'm using the percentage to make this into a decimal. 6.024. And let's see what it says for 7 or more. 0.014. And I'm going to enter that. I've now loaded that into my calculator. This is the first time we've done this, and this is something that we will do many times. So we just completed that second step where we loaded the x values, the random variables, into L1, and we loaded the probability of each of those random variables into L2. We're now going to go back into the stat menu, and we're going to go over to calculate. And in the calculate menu, we're going to leave 1 variable statistics selected. Notice that that's our first option, and I'm going to press enter. So our first list is L1, so that's the random variables. The frequency is the probability of that random variable occurring. So I arrowed down to get opposite that question. Now I want to get list 2. So look at your calculator and look right above the 2 on your calculator, and in blue you'll see L2. Blue means that I have to press the second key and then 2 to get L2. Then I'm going to enter to calculate, and it tells me everything I could possibly wish to know. The x bar, the mean, is 2.52. The standard deviation is 1.416. Notice that n didn't add up perfectly to 1. In other words, when we added these up, it actually added up to 0.999. But that's good enough. It knew what we were doing. So our first look at using our calculators for a discrete probability distribution. If you're using a TI-83, when you select 1 variable statistics, it will actually appear on your home screen. You'll then enter L1, L2, exactly as we did for the 84, in other words, using second 1 for L1. There's a comma key right above the 7 on your calculator, and then second 2 for L2. The rare event rule in classical statistics is basically an assumption, a philosophical assumption, that if something is very unlikely, that is, if the probability is extremely small, then the event is probably either unimportant or the data that was collected is not correct. In other words, maybe there's something wrong with the data. Now there's 2 ways that an event could be unusual. It could be unusually large, or it could be unusually small. So in the first case, we're going to look at unusually large numbers of results. So if you're looking at x successes among n trials, and the probability of x or more successes is less than 5%, then you can consider x to be an unusually high number of successes. So we're not simply looking at the probability of x. We're looking at random variables that are at least that large. So that large or larger. So we need to add up all of those and compare that to 5%. So another way to think of this is if the probability of at least x successes among n trials is less than 5%, then the event is considered unusual. And again, at least means as large as x or larger. You can think of this as not talking about the exact probability of the random variable x number of successes. You can think of this as being as extreme as x. So if you're looking at a value of x that's large, you have to consider all the values larger than it. Similarly, if you're looking at x successes among n trials, and the probability of x or fewer successes is less than 5%, then you can consider that random variable x to be an unusually low number of successes. So if when you look at a random variable and you say, well, that's a small number of successes, then you need to consider all the random variables smaller than it, and that includes 0. Another way to think of this is if the probability of at most x successes among n trials is less than 5%, then the event is considered unusual. And here the key phrase is at most x successes. So we're basically saying this looks like a small number of successes, but we need to consider not just that particular exact value for x, but everything smaller than it if we want to say that that is an unusually low number of successes. So let's look at an example. Let's compare our family size data and ask the question, is it unusual for a household to have 6 people in the family? Well, when looking back at the household size distribution, we can see that the probability of having 6 people in a family is 2.4%. But we're basically asking the question, is that an unusually large number of people in a family? If so, we have to look at all the families larger. In other words, we have to also include the probability that the family has 7 or more people in it. So when we ask this question, we have to take the probability of having 6 people and add the probability of 7 or more to that. That's still less than 5%, so yes, this is an unusually large size for a family in the United States at the time of the 2010 census. If you did come upon many families that had 6 people in the family, what would you think? There's lots of ways of thinking about this, and the first that I thought of is that according to the census, that is not likely to last for long. That is, it may have had 6 people in it to begin fewer people to begin with, climbed up to 6, and then some of those people will move on. The other way of looking at this, of course, is that family size is largely a function of culture. Having aunts and uncles and parents and other siblings, nieces and nephews living with you is probably more common in some cultures than in other cultures. Similarly, some families are simply very large and their children live with them for a long amount of time. So there's lots of ways of looking at this. It's not necessarily 2 adults and 4 children. It could be 2 siblings and an aunt and their grandparents and maybe a parent. There's lots of ways that this could happen. But if you came across many families like this, I think the simplest explanation would be that it's part of a progression. They are currently have a lot of people in their household that will increase to 6 and then decrease, or it might simply be a cultural attribute. Is it unusual for a household to have 4 people in the family? Well, let's look back at our data. So unusual to have 4 people in the family. Now, I don't have to worry about adding up the probability of having 4 people to 5 to 6 to 7 because I'm already over 5%. So this one's a lot easier simply because I look at 4 and I'm already over 5%. So this is going to be relatively straightforward. Nope, it's not unusual. If you came across a family that had 4 people in it, what would you think? I'd say it's not unusual. The family size probably was lower earlier and then will become lower again. Another thing to point out, there's a lot of ways of having a household with 4 people in it. Again, think back to nieces and nephews, aunts and uncles, parents, grandparents. Lots of ways that a family size can have 4 people in it. So it might be temporal, it might be the fact that there's just many different generations. So our next section is 5.2, and now we're looking at a different kind of discrete probability distribution. We're looking at a binomial probability distribution. We saw a little foreshadowing of this with the orange tree question in the handouts. We're now developing this idea fuller. A binomial probability distribution is different from just a discrete probability distribution where you go out and collect the probability of each one. And that's because the results come from a fixed probability. So 4 things have to happen before you can get a binomial probability distribution. There has to be a fixed number of trials. That's almost certainly n, and that experiment is repeated a specific number of times, n times. Now the reason for this is simple. If you simply allow n to get larger and larger until you get the result you want, or until you get closer to the result you want, you're kind of cheating. You need to fix the number of trials to begin with. The next requirement is that the n trials are independent, which means that what happens in one trial does not influence the outcomes of the other trials. Now, this may seem kind of obvious, the idea that if you perform an experiment, there's really no way that that information should move from one experimental subject to another. But really, this is about randomly selecting the members of the experiment. If you don't randomly select the members that are being observed, that are receiving a study, there is every likelihood that you're going to get a cluster that have similar views, similar genetics, similar histories. So this question is really about choosing the sample well. And in a classical statistics course, we usually get around by simply saying that the selection process was in some way random. The next requirement, the third requirement, is that there's only 2 outcomes, which are called success and failure. And that's the words that are used. There is no value judgment here. It's just whatever you're counting is successes, and whatever the other stuff is failures. Now, the other way of thinking about this is that the probability of a success does not change from trial to trial. In other words, we're not saying this is the probability for a household of 1 person, for a household of 2. We're saying that that probability of success stays the same throughout. So remember that P is the probability of success, Q is the probability of failure. So they're simply the complements. P is the thing we're counting, the probability that it happens, Q is everything else. The binomial formula for probability says that the probability that the random variable is R, so whatever that particular number is the number of ways you can arrange R things among n. And then if we've got R successes, the probability of that happening was p to the rth power, that's the multiplicative rule, and we multiply that by q to whatever's left. N minus R is all the other trials. And then there's a reminder of the formula for combinations, n factorial over r factorial and minus r factorial. Now the r factorial in the denominator simply ensures that order doesn't matter. Remember that C for combination is the same as C for a committee, where order does not matter. So let's look at this. If we look at the p's and the q's, p to the r and q to the n minus r, that is the probability of getting r successes among n minus r failures. And the combination, n choose r, is the number of ways these n successes can be arranged, or the r successes can be arranged among the total of n. So binomials on the TI. So the first thing to point out is that there are 2 binomial distribution functions. There's a PDF and a CDF. The P stands for probability, the C stands for cumulative. So one of the things that I've done in your workbook is I've made the P's bold and the C's bold because you have to get the right one. So binomial probability distribution functions and binomial cumulative distribution functions. Both of these are in the variables, or the variables button on your calculator that when you press second gives you distributions. This is very similar on a TI-83. You'll conjure up the binomial probability distribution function from the menus, and then you'll list n, the probability, and x. That comma key is right above the 7 on your calculator. So binomial probability distribution function calculates the exact number of successes. So whatever you put in for x is what comes out as the probability. Cumulative distribution function calculates the cumulative probability. So it asks what is the probability of between 0 and x successes, which again is the same as asking what is the probability of at most n successes. So two different places in our calculator. So the screenshots are from our next example. I'll pull up the calculator and step you through this on the next page when we see them. But it's nice to see the difference between a probability distribution function and a cumulative distribution function. So I'll lay it out. We're also going to need to talk about the difference between at least and at most. So we're going to consider a binomial probability distribution with 17 possibilities. So here they all are. Notice that it starts at 0. You might have 0 successes, nothing that it is that you are counting. So among these 17, let's ask the question what different things would look like. For example, what does at least 11 look like? Well, at least means the smallest thing that would accept is 11. So we'd certainly be happy with 12, 13, 14, all the way up to 17. So at least 11 is 11 or more. At most 10 says that 10 is the largest thing that we would be happy with. So we'd be happy with 10, but we'd be also happy with 9 or 8 or 7 or 6, all the way down to and including 0. So if I notice these two things, that together 11 through 17 and 0 through 10 is everything. In other words, everything is either one or the other of these. At least 11 is the complement of at most 10. Now, that's useful to us because we know how to use our calculator to get cumulative distribution functions. Let's look at an example where we've got 20 people and we're told that 1% of people in the world have green eyes, and we're interested in the binomial probability distribution. So what's the random variable? Well, we might as well just say the number of people with green eyes. Is this a binomial experiment? Well, there's a fixed number of trials. There's a group of 20 people. The second I have absolutely no idea about. Is this sample random? If it is, then maybe the outcomes are independent. If it's not random, if it's not a random selection of people in the world, then I might be over-selecting people from a particular geographic region. The third requirement is that there are only two outcomes, and I certainly would agree with that. Either a person has green eyes or not. I'm not quite sure if you can have two eyes of different colors. I know dogs can have that. I've seen it in one of my friend's dogs. I'm not sure if it happens in humans. So let's simply say both eyes are green if that becomes an issue. The probability does not change from one person to the next. Well, again, if the sample is random, then I can probably assume that. But if I'm perhaps in Ireland, if I'm perhaps in a different part of the world, I'm not so sure that that sample would be random. So if it is random, then I can probably say that eye color of one person does not tell me what to expect the eye color of the next person to be. It says, find the probability that none have green eyes. So let's first go through and use our formula. Our formula says, find the probability that the random variable is 0. The n, the number of trials, is 20. We want to figure out how to arrange 0 successes in 20 things. Well, that's going to give us 1. There's only one way to have 0 successes, and that is if we have 20 failures. We then take the probability of success and raise it to the number of successes. 0.01, that is 1%, to the 0th power is another 1. In other words, that didn't accomplish anything. And next we have to take the probability that someone does not have green eyes, 99%, and raise that to the 20th power. That is, everyone in this sample has eyes that are not green. So the question becomes, what is 0.99 to the 20th power? And according to our calculator, it is approximately 0.8179. Let's see that done in our calculator. So let's do that by getting back to the home screen. So second, quit, and then entering 0.99. I'm going to raise that using the exponent key, the caret key, to the 20th power. I don't need to get out of the exponent, so I'm simply going to leave the cursor up there and press enter. Now notice that we could have also gone into the distribution menu by pressing second and then variables, or to get the distribution menu, and go down to a binomial probability distribution function. So the PDF, press enter. There were 20 trials. The probability of success was 1%, so 0.01. The number of successes, the random variable, was 0. And let's paste that in and have it do it, and we get the same answer for that as well. The next question asks us to find the probability that 9 have green eyes. Having green eyes is very rare, and 9 is about half of the sample size, 20. So I'm concerned that this is a kind of silly question, not something that would happen very often. So let's go through and do this. We're interested in finding the probability that the random variable is exactly 9. So we're going to say 20 choose 9 times 0.01 to the 9th power times 0.99 to the 11th power. So let's do that in our calculator. So I'm going to enter n, so there's the 20. I'm going to go into the math menu, over to probability, down to NCR, and enter 9. I want to arrange 9 things without concerning myself with order among 20. So that looks like it happens 167,000, almost 168,000 different ways. I'm now going to multiply that by 0.01 to the 9th power. I need to get out of the exponent, so I'm going to arrow to the right. I'm going to multiply that by 0.99 to the 11th power and press enter. Now this is not 150% because of that exponent of negative 13. The negative means that this is being divided by 10 13 times. That's the same as moving the decimal point 13 times to the left. In other words, 0.000, and I'm not going to say it because I didn't start counting, but 12 zeros between that decimal point and the 15038. That is vanishingly small. And let's see where that tininess came from. It came from the 0.01 to the 9th power. So here's that 0.01 to the 9th power. That's a tiny, tiny number. And you might say, well, yeah, but we're multiplying it by almost 168,000. But that only has 1, 2, 3, 4, 5 decimal places in it. This is taking us 9 decimal places to the left. And of that, we only get to keep, because we're multiplying, 98.5% of it. So this does indeed work out to a number that is essentially 0. Let's go through and do this again with our calculator's built-in functions. So I'm going to press second and vars to get into the distribution menu. I'm going to go down to a binomial probability distribution function. I'm going to say, yep, there's still 10 trials. The probability of success is still 1%. But now I'm interested in 9 successes, so I change that 0 to a 9, paste it in, and I get the same very, very small number in the sense that it's close to 0. The next question says, at most 3 have green eyes. So at most 3 have green eyes means that would be okay with 0, 1, 2, or at most 3. So we're talking about actually 1, 2, 3, 4 different cases. Don't forget the 0. We can do this in our calculator if we remember that this is exactly how a cumulative distribution function looks. So we're going to go into our calculator. We're going to go into the distribution menu. So second vars to get into the distribution menu. We're going to go down to a binomial cumulative distribution function. We're going to say there's still 20 trials. The probability of success is still 1%, so 0.01. We're now interested in up to, at most, 3 successes. So we're enter a 3 for the x value, and then we paste that in and press enter. Well, at most 3 folks with green eyes is really likely. So when we look at the probability, and we actually look at how many 9s there are in this number, if we're rounding this to 4 decimal places, that rounds to 1. We're almost certain to have at most 3 people with green eyes. Again, assuming that this is randomly chosen from the people in the world. At most 2 have green eyes is a very similar question to the one that we just did. So we just did a question at most 3 have green eyes. So here we're interested in 0, 1, or 2 people with green eyes. We're going to go into the cumulative distribution function again, but change the number of successes x to 2. So let's do that on our calculator. We're going to, well, I'm going to just arrow up to grab what we just entered so I don't have to go into the menus. I'm going to arrow over to the 3 and change it to a 2 and press enter. I pressed it twice and I got the answer twice. 0.9989964 and change. And this one, if we round to the nearest 4 decimal places, we get 0.9990. The next question asks us what is the probability that at least 4 people have green eyes. This is not something that we can compute directly with the binomial cumulative distribution function. Remember that it starts with 0 and goes up to x. But we can use the idea that these are complements. So what we're going to do is we're going to say, well, what does it mean to have at least 4? That means we're fine with 4, 5, 6, all the way up to the total number of trials. Now, that means we're talking about everything but 0, 1, 2, and 3. So we're going to say everything, that is 100%, except the probability that x is less than or equal to 3. So we're using the complement here. What we're interested in is the probability that x is at least 4. So what we're going to do is we're going to find the probability that x is at most 3, and we're going to take 1 away from that. So when you're looking at your workbook, make sure you see the 1 minus in both of these. So 1 minus the cumulative distribution function and 1 minus what we've got there. So let's take a look at this in our calculator. So I'm going to re-enter this from scratch. So let's do 1 minus. I'm going to go into the distribution menu. I'm going to go down to a binomial cumulative distribution function. You could have just pressed B to get there. So trials, still 20. The probability of success, still 1%. I'm interested in the cumulative distribution function up to 3. And I'm going to paste that in and have it perform the arithmetic. And it's basically saying that this is vanishingly small. That 5 means that there's 4 zeros between the decimal point and the 42620, which means that if we round to 4 decimal places, we're going to get an answer of 0. It says in Europe, 4 people out of 20 have green eyes. Is this unusual? Now, we're assuming that we're asking, is this unusually high? So that's the first thing that I would point out. If green eyes are randomly distributed at 1%, you'd expect 1 out of 100 people to have green eyes. So remember, to be unusual, we have to ask if the probability of all the values that are at least that extreme have a probability less than 5. At least that extreme. Since green eyes are relatively rare, we're asking if there are an unusually high number of people with green eyes in Europe. Recall that if the probability of X or more successes, 4, 5, 6, 7, 8, all the way up to the total number of 20, is less than 5%, then you can consider that X value to be unusually high. So therefore, we're going to use the information that we just computed. We just computed that the probability that X is 4 or more, that is at least 4, is 0. So that means adding up all those probabilities, the probability that there's exactly 4 people with green eyes, to 5 to 6 to 7 to 8, all the way up to 20, and we get a probability of 0. That's definitely less than 5%. So we can say that the incidence of green eyes in Europe is unusual. Okay, some very similar questions. This is in many sense almost identical to what we did with the green-eyed questions. So this page and the next are kind of a review. I'm going to go a little bit quicker. The new stuff comes after this. So 1 in 88 have autism. A group of 10 children is perhaps randomly selected. So let's state the random variable. X is the number of children with autism. We're considering that the success. We're certainly told that there's a fixed number of trials. There's 10 children. We have no reason to believe that this collection of 10 children is random. Therefore, we have no reason to believe that the probability of randomly selecting one child with autism won't affect another. Now, you might be saying to yourself, I said exactly that same thing or something very similar when we were looking at the 20 people who have 1% chance of having green eyes. And I said at that point that I didn't see that it was randomly selected, so there's no reason to believe that it represents that 1% number. So you might say, well, that means we can't do it. And generally, that is exactly how we should respond to this information. But several points over this semester, we will discover that something didn't work. One of the great phrases that Kate has in her book is basically, she says, if the test then fails because you didn't perform everything you needed to as a prerequisite to performing it, then it's your fault. And I think going into statistics, that's about the right way to think. People are relying on you to get valid information. So you really do need to check that what's coming to you is also valid. Step 3 asks us, are there only 2 outcomes? And we're going to say yes, either a person has autism or not. So we're simply going to make that binary. The probability does not change from one person to the next. That's if the sample is indeed random. Then the incidence of autism does not affect another child in the study. Find the probability that none have autism. Well, this is exactly what we did in the green-eyed question. The probability that X is 0. So we're arranging 0 things among 10. There's one way to do that. We're raising the probability of success to the 0th power because we're looking for 0 successes. We're raising the probability of failure, 87/88, to the 10th because everything is a failure in that sense. And we see that it happens almost 90% of the time, 89.2% of the time, that in a randomly selected group of 10 children, there's no one with autism. Let's take a look at this on our calculator. So we're going to get a cumulative binomial probability distribution. So I'm going to go into the distribution menu and get a probability distribution function. I'm going to put in that n is 10, that the probability is 1/88. One of the cool things about your calculator is you can input an expression there. So you can actually say, hey, whatever the number you get when you divide 1 into 88, that's the probability of success. And we're interested in 0 successes. And when we paste that in, we see exactly that number. The next question asks us what's the probability that exactly 7 have autism. So if we put this in our calculator, the probability that x is 7 is 10 choose 7 times 188 to the 7th times 87/88 to the 3rd. So let's go through and do that. I'm entering n. Then I'm going to go into the math menu over to probability to get NCR, the number of combinations. We're interested in arranging 7 things among 10. That happens 120 ways. I'm going to multiply that by 1/88, and I need those parentheses because of the order of operations, to the 7th power. And I'm going to multiply that by 87/88 to the, let's see, 3 are left, so 3 failures in that particular situation. And there's 11 zeros between the decimal point and the 2837. That exponent is -12. It tells us to move the decimal point 12 times, making this number really, really close to 0. Let's go in and do this again with our calculator. I'm going to arrow up and grab a probability distribution, making sure that that's a P, not a C. And then I'm going to go change the number of successes to 7. Press enter, and there you have it. We've got exactly what we calculated when we used the formula. The next question says at least 5 have autism. At least 5 means 5, 6, 7, all the way up through 10. That's the complement of at most 4. So we're going to compute the probability that there is at most 4, and then we're going to take its complement by saying 1 minus that. So let's go into the calculator and do that. I'm going to go into the distribution menu, down to a cumulative distribution function. I'm going to say, well, there are 10 trials. The probability of success is 1/88, and we're interested in 0 through 4 successes. Now, when we plug this in, this is not the number that we want. This is the complement of the number we want. So we're going to say 1 minus, and then get the answer from the previous question, second ANS. Press enter, and again, a number really close to 0. There are 7 zeros between the decimal point and the 4553. The exponent is -8. So the probability of at least 5 of these 10 children having autism is vanishingly small. The next question says at most 2 have autism. Well, our calculator can compute this as written. This is asking us for the probability that there's 0, 1, or 2 successes among those 10 trials. So again, we're going to use the binomial cumulative distribution function. We're going to ask it to add up the number of successes between 0 and 2. So let's go and grab the cumulative distribution function. I was just using it, so I'm going to go up there. And let's change that 4 to a 2 by arrowing back over the 4, changing it to a 2. And it looks like that is exceedingly likely to happen. So in a randomly selected group of 10 children, if the background statistic is correct, would expect 99.98% of the time to have at most 2 children with autism. The next question says, suppose that you find 5 out of 10 children have autism. Is this unusual? And again, we're basically saying that this looks like an unusually high number of autistic children in this group. So therefore, we're going to ask the question, if X or more successes is less than 5, then we can consider X to be an unusually high number of successes. And remember, we've already calculated that, and we decided that it was vanishingly small, certainly less than 5%. So we can indeed say that if the group is randomly selected, 5 children with autism is unusual. Because the probability stays the same throughout all n trials for every participant, each roll of the die, the probability of getting a 6 is the same, doesn't change. The finding the mean and finding the standard deviation, which is much more involved for a non-binomial discrete distribution, is actually very easy for a binomial distribution. Take a look at these two formulas. Now, before you say, why didn't I use these formulas earlier? These are so much nicer than ones with capital sigma in them, where I have to find the difference and square it and multiply by probability and then add all that up. There's no sigmas in this. This is just two operations in the case of the mean, and 1, 2, 3 in the case of the standard deviation. One operation in the case of the mean, actually. So easy peasy. This is true because a binomial distribution is so highly structured that probability of success does not change. Now on the next page, we're going to look at our first example of an entire binomial probability distribution. Not just one result, not just 0 or 5 or some particular value, but everything. So let's go there, and then let's come back and see how to get that out of our calculator. So again, we're looking at 20 people. Again, we're saying that if that group is randomly selected from the population of the world, we can expect 1% to have green eyes. I copied and pasted. The random variable x is the number of people with green eyes. Again, we have to be concerned with independence. We're not told that this sample is random, so therefore it may not be independent. We may have oversampled people from different parts of the world, where the incidence of green eyes is not the world average. There are two outcomes. Either a person has green eyes or not. The probability does not change. Well, that's assuming that the sample is random. The classical statistical emphasis on random has largely been replaced by a different way of thinking. Instead of random, representative. So something to think about. It says write the probability distribution. I'm going to do this in our calculator because it is so much easier than computing these separately. It's not a big deal. You can definitely compute these separately. So if you're thinking to yourself, well, that's easy enough, I'll just arrow up and change the number of successes and press enter again. That really does work well. But I want to show you another way to do this. So I'm going to go back to the previous page because there's plenty of room there, and I'm going to pull up our calculator and I'm going to show you how to do this. So we're going to turn it on. We're going to go into statistics. The default is edit. We're going to leave it there. We've got this was from the household size. So I arrowed up. So make sure that you see that I arrowed up from the 1 to the L1, and I'm going to clear. So all that household data I'm taking away, and in its place I'm going to put in 0. So I press 0 and then enter. Doesn't like that. So let's go to see what didn't like that. It didn't like that because I can't say that a list is 0. Okay, so I need to clear and I need to arrow down. Okay, so now that I've arrowed down, I can start to enter the number of successes. So I'm going to enter 0, 1, and you say this is boring, and I say this is the boringest part. 3, 4, I might just pause and finish loading this data all the way through 20. So I loaded L1 with 0 through 20. So I've basically put in all the potential random variables. I'm now going to arrow over to somewhere inside of L2, and then I'm going to arrow up to L2 itself. I'm going to press clear, and I'm going to arrow down. Notice that there's no more L2. And you might say, well, now the hard part is to compute the binomial distribution function for each of these. So I'm going to do that, and I'm going to do it in one fell swoop. I'm going to arrow up again, and I'm going to press enter so that the cursor is now blinking after L2. I'm then going to go into distributions. I'm going to go down to the the probability distribution function. I'm going to say that there are 20 trials. I'm going to say that the probability of success is 1%. And then for the x value, I'm going to say grab whatever the value is in L1. So second 1 gives me L1. And I'm going to paste that in. And then I'm going to press enter. And it takes a little while, but it completes that entire column with the probabilities of each of these random variables, which is just super cool. So let's take a look at this. First off, remember you have to start at 0. What you can call it a success, you can call it whatever you like, but you have to start at 0. And then notice we got a bunch of numbers that are kind of interesting to begin with, but rapidly become somewhat useless. That scientific notation there is not really all that helpful. So notice that fairly soon these numbers become zeros. So here's our binomial probability distribution. So I'm going to uncover that. So lots and lots of zeros. In fact, it looks like beginning at 5, those become zeros. The next thing it asks us to do is to draw a histogram. I used R to do that. At the very end of the video, I will show you how to do this in R. If you say, oh, that's a simple enough matter, I could do that. Just 0 has 0.8 approximately, 1 has 0.2, 2 looks like it's down there almost vanishingly small, and then zeros all the way across. You could sketch that. Now the next question asks us to find the mean, the variance, and the standard deviation. This is a binomial distribution, which means that we can use our excellent new, Our excellent new formulas for binomial distributions. N times P gives us the mean, N times P times Q inside the square root gives us the standard deviation. So for the mean, N is 20, P is 1%. 1% of 20 is 0.2. The mean number of people that we would expect to have green eyes is 0.2. Now the variance is the standard deviation squared, so that's N times P times Q, which works out to 0.198, fairly high variance. And the standard deviation is just the square root of that to get rid of the square. And when we take the square root of 0.198, we get approximately 0.4450. So I made this into a spreadsheet, then I made that into a list with the comma delineation. Then I put in the R code for this. I decided to call it binomial probability distribution, so BPD. And then there's the command to make a bar chart. Okay, I launched R, and now I'm going to copy and paste data from the spreadsheet into R. So in the workspace, I'm pasting that in. Press enter so that it latches. It says that I've got the BPD data loaded. I'm now going to give it the command to create a bar chart. So back into R, paste that in, and there is our bar chart. So what I did is exported it. So I clicked on export and I just copied it to the clipboard, and then I pasted it into the file that I'm using to make this. So really easy to make a bar chart in R.